much. So I want to talk about some, if I can get it to work, sorry. So, so the talk here will have a couple of themes. So I want to talk about the geometry, including sharp bounds for the set of singularities. And then from an analytical point of view, and that's sort of, in a way, the main focus on these two, the lecture today and the lecture tomorrow, is optimal regularity. And it will largely be about optimal regularity, about a degenerate, classical, one of the classical degenerate elliptic nonlinear PDEs. But I will also talk about some applications to other equations. And so this is joint work. This is all joint work with Billman and Coxeter. And so just to review, so we're looking at here at a one-parameter family of hypersurfaces, MT, that are flowing by the mean curvature flow. So the derivative of the position vector is given in terms of the mean curvature and is moving normal to the hypersurface. So the speed is minus the mean curvature and is moving normal to the hypersurface, right? So h is the mean curvature, n is a unit normal. And so the avoidance principle that we talked about, which was a geometric formulation of the maximum principle, the avoidance principle was this principle that said that if you take two hypersurfaces and they are initially disjoint, and if you flow both of them, then they will stay disjoint. So, right as we discussed yesterday, a consequence of the avoidance principle is that if you take a closed hypersurface, you enclose it with a large round sphere, then the sphere becomes extinct in finite time, so the hypersurface becomes extinct in finite time. So the hypersurface will, at some point, it's not really a surface anymore, so that you will reach some singularity. So singularity happen. And so the key question is, so we discussed a little bit this yesterday, what are the singularities? What is the set where the singularity is formed? So this is the key sort of geometric questions. I'll get to the analytical formulation shortly. So, and also just to review a couple of examples. So we talked a lot about what happened for curves in the plane. For hypersurface, I'll just illustrate this again in two dimensions. So here are some simple examples. Thin torus of revolution. If you're looking at it, as it's evolving, well, it's rotational symmetric. So under the flow, it will remain rotational symmetric. You get just one singularity, and this is a whole. In this case, it would be a whole circle of singularity. And the singularities are cylindrical. So by that I mean that imagine that you run the flow here. This torus here is the width, the sort of cross section here of the torus is shrinking. But so this means that if you're looking at a point right before it becomes extinct in a circle, if you're looking at it right before and you kind of try to enlarge the picture, well, if you enlarge it, sort of torus will blow up to infinity, and you will see just on a very large part, it will look like a cylinder, right? And so that means that is what it means, that the singularity is cylindrical, that you're looking at this kind of blow up, and if you right before a singularity, and if you blow up as you're approaching the singularity, then actually in the limit, as you rescale to unit size, you just get, in this case, you just get a cylinder. So that's what it means to have. Sorry? Yeah.
Which is, you take the wedding ring.
Yep.
It's positive mean curvature on the outside, so that goes in. It's negative on the inside, so that also.
Well, this. Yeah, it is shrinking.
So what has to win is the small diameter has to shrink faster than the large diameter.
Yeah, that's right. Yeah, that's right. Exactly. That's right. And absolutely, that's right. Yeah, this is actually, and so in fact, I mean, I'll say more about this. So this example, as you say, is mean convex. And the dumbbell I showed was also a mean convex dumbbell. And this will play a role later on. That's how you arrive at an elliptic equation. And we'll talk about that. There's something called the arrival time. And we'll talk about that in just a minute. Okay, so the other example I wanted to review is this dumbbell. So this is example of gradation. And so you have this dumbbell, you have this bar, thin bar between these two bells. You're flowing it. I looked at it where it has, so this particular example, it's actually also symmetric around a plane here, right? So it has a reflection symmetry also. So the two bells have the same size. And so in this case, there are three singularities. There's two singular times. There's a singular time where the neck is pinching off, and then there's a second singular time where each of the bells, so the neck is pinching off. We'll see the time shots a little bit later, but just if you may recall from yesterday that the bell, the bar here is first pinching off, and then each of the two components here become instantaneously smooth. They will become round and then eventually disappear. And so you're getting three singularities, but two of the singularities happen at the same time because the bells have the same size. The first singularity, if this is where the bar here is pinching off, if you're looking right before that singularity happened, you again rescale the surface to unit size. The bells here is blowing off to infinity, and then it will look almost like a perfectly round cylinder. Right, and so the first singularity is cylindrical. The two later singularities are actually where these bells are disappearing, and they are spherical. If you rescale the surface, each of these components to unit size, they will look almost perfectly round. Okay. Now, so we've looked at, so the simple examples we looked at were the sphere, the cylinder, then the marriage ring. Maybe it should have been called the wedding ring, but it's usually referred to as a marriage ring. And the dumbbell. The dumbbell is the only of those examples where there is a singularity and where the whole surface doesn't appear at the singularity. So in order to understand what it means to flow past singularity, then one needs some weak notion of the flow. And so there's two approaches. There's a weak solutions, and we'll talk about them in just a moment. So there's weak solutions to the flow, where you can flow past singularity. And there's another more recent approach where you are performing surgery, and then you you have a sort of surgery procedure and a surgery parameter, and you do smaller and smaller surgeries, and then you look at some limit of those. Right? So in the second case, the surfaces remain smooth all the way along, but you let the surgery parameter goes to 0, and so as you do this, in the limit, you're getting some singular object. So we're focused on the first one. And there are three different versions of those. So three different versions of weak solutions. The first one was one due to Bracke. This is a geometric measure theory approach. Then there's a version that was pioneered by, so the second one was pioneered by Osher and Setien and Evans, Spook, Chenkik, and Godo. It actually go back, sort of the notion go back further. There's references to it already in the material science literature. And then there's a third notion of De Giorgi, using barriers. And so we will use this second notion, this notion of Evans-Brooke, Chenki-Gengodo, and Osher-Setien. And so that's what I want to talk about here. And so that is the level set method. And so here's how the level set method works. That you have, suppose you take a hypersurface. Now choose a function, and let's say that that function vanishes on the hypersurface, and in the domain that is hypersurface bound, it's positive, and in the domain outside the hypersurface, the function is negative. Okay. Now you want to flow each of the level sets of this function. Right? So you flow them simultaneously. And so you flow them simultaneously. By the avoidance principle, these level sets of the function will remain disjoint. Okay? And so this is a level set method that has been extremely useful numerically. So this was numerically the first important work on this numerically was due to Osher and Setien. I'll get to this in a second. I mean, of course, this is we'll talk about this. That's why the equation is degenerate, right? Because it actually is, we'll get to this in just a second. But actually, it's impossible to have that the gradient is. I mean, there will be points where the gradient vanishes. Those correspond to singularity. We'll talk a lot more about it, and that's why the equation is degenerate, because you are asking to divide by the norm of the gradient. So you're asking to divide by something that's zero. That's what it means for the equation to be degenerate. So again, the level set method has been extremely useful numerically. Here are some examples. I mean, I just looked. I gave a talk a little over a year ago about it, and just since that time, there's about 1,500 more citations to this paper. So it's extremely widely used. And the mean curvature flow is sort of there's a whole class of evolution equation. The mean curvature flow is sort of the poster child for this family of evolution equation. And so this is a picture from Setien, so where you are. So the level set method is all about that you have something that is evolving over time. You're trying to track the perimeter of it, or the front. And so this here is an example of Setien where you have a forest fire, and you're tracking the perimeter of the fire. In this case, two different components of the fire merge. So this is not mean curvature flow, but this is just in this sort of family where you have, So the mean curvature flow again sits inside a larger family of flow where you are tracking, fronts that evolve over time, and typically the speed is curvature dependent. This is sort of the classical, and the most classical of those is where the speed is exactly the mean curvature, and that is the mean curvature flow. So it's there's all kind of other equations. The simplest of these equations is this equation, which is just the distance, right? The Ekinov equation. I hope Ekinov. It's an Ekinov. I now forget the name. Is it Ekinov? Ekinov. Sorry. Right. That's the simplest, and that's where you have a set, and the level sets are just the distance from that set. Right. Right, that's right. Exactly. Flowing the distance one out. It's a little bit like this. Yeah, exactly. Right. So that's another one in this family. Right. Okay, so and here's another example of this where you're tracking a front. Here you have these droplets of oil on water, and you're looking at the perimeter of the droplets, and some components merge and others spread apart. And here again, this here is a sort of this is actually taken from, this picture is taken from Wikipedia, that illustrates how the level set method works. Sorry? Right. That's right. That's right. There was actually, I gave some talk at one of these big AMS meetings where there was some guy that wanted to have some application to some I think we were Australian, and he wanted to know something about fires in Australia, and I wasn't quite able to solve that. Okay, so the level set method it was used numerically very successfully by Osher and Session in a paper in '89, but the analytical foundation for understanding the equation was provided by Evans and Sprook, and independently at the same time by Chen, Giger, and Godot. And so what they proved is they proved existence of Lipschitz viscosity. So these are these weak solutions to the equation, because the functions are just the equation. We'll come to the equation in just a second. But it's a second order equation. They just prove, you can make sense. So they made sense of that you have solutions to this equation in a weak sense, in this viscosity sense. And they proved that the solutions are Lipschitz. They also proved uniqueness. So for given boundary data, you have a unique solution. And they proved that solutions agree with the classical solution. So if the evolving front stays smooth, then this weak notion of solution agree with the classical notion. And so this work of Evans and Sprook, Chen, Giger, and Godot was one of the major success of this notion of viscosity solution of Mike Crandall and Pierre-Louis Lyons. But I should also say, somehow I feel obligated to say that there are two different notions of viscosity solutions, and they are different. There's another earlier notion that probably a lot of people know of Calabi. That's also a notion where you're talking about where you can make sense of that functions are solutions. But that one is slightly different than it's actually a different notion but the spirit is the same. And I think they were unaware of this notion. But the notion that we're using here was given by Mike Crandall and Pierre-Louis Lyons. Sorry? Yes, that's right, and that's right. I talked with Craig about it. There's some earlier paper also of Craig, and so Craig, yeah. I mean, I don't know if you should get into the history, but so Craig, of course, very generous person. He was saying that uniqueness is really the key, and Crandall and Pierre-Louis Lyons was the one that actually got the uniqueness. So I want to ask him about it. But you're absolutely right. Okay, so now we come to this that Walter was talking about. So let's look at the case where the front is moving in a monotone way. So this is also numerically, this have been modeled numerically extremely efficient, in this case, by something called the fast marching method. So if the front is moving, so you have this hypersurface, and if the front is moving inside, so if it's just at the beginning, it moves inside itself. Then this, in geometric terms, correspond to that the mean curvature of this hypersurface is positive. Under the flow, by the maximum principle, this condition here is preserved. So if it's initially is moving inside itself, it will keep moving inside itself. Right, and so here's an example again that we talked about earlier. Here you have this. This is of course in the case of curve, but you would also imagine that this is a hypersurface. Now we don't. This is in the case of curve. Mean convexity is of course the same as convexity. For hypersurface, it is of course much weaker. I'm talking about it as if it was in R3, but it could really be any dimension. And so here, right, again, the outer one is the initial one. The ones inside here are at later time. So as you're going, it's like a tree. As you're going inside here, it's like the oldest part of the tree. Okay, so by result of evidence of spoke, Chen, Giga, and Godot, if the mean curvature is positive initially, it moves inwards, keep moving inwards, and it sweep out the entire domain that the initial hypersurface bounds. In this case, one also know that singularities are either spherical or cylindrical. Here's an example of and sphere. Maybe I should just say a little bit about this again. So what one knows is that they're spherical or cylindrical. This just means that if you're looking right before a singularity, if you enlarge the picture, then it will look like the surface will look like either a sphere or a cylinder. Again, here it's in any dimension. So a cylinder is what I call a generalized round cylinder. So it's a Euclidean factor cross a sphere. The Euclidean factor could have any dimension, right? And again, and this has been known for quite some time. This important point here was that it's a kind of one of these weak results. It's weak in the sense that it looks like a cylinder. By the most sort of complicated cases, in the case of a cylinder, if you look at that, it looks like a cylinder. But what cylinder look like may depend on how much you're blowing up. So if you are looking at a later time, but still right before the singularity, and you rescale, you could get a different cylinder. Okay, so it just means that if you blow up, you get a cylinder, but as you're blowing up on a small scale, the cylinder could have rotated. Okay, so a priori it could rotate around. We'll rule this out, and it turned out that the key that if you can rule this, that once one have ruled this out, that's the key to proving optimal regularity. Okay, but that's a kind of this sort of notion is a sort of famous notion in geometric analysis. This possible non-uniqueness. So by fairly weak general compactness argument, you can get a blow up with some nice property. But a priori, this blow-up depends on how you rescale. Okay?
Can't get across.
Right. Not in this case. In this case of mean convexity. Right. I'll talk a little bit about other in the case. Yeah, while H would not actually, just so in this case here, I'm looking at where the initial hypersurface is mean convex. Mean convex, I was saying that it means positive mean curvature everywhere. It just needs to be positive at one point by the strong maximum principle. Okay, so now when the initial hypersurface is mean convex, then we know now that under the flow, the hypersurface move inside itself, and it keep moving inside itself. So this here is also taken. This is a simulation of Sethian, and so this is for the dumbbell. So this is really a cut in the dumbbell line. You should imagine that the sort of surface is rotational symmetric, And again, the outer one, this is the initial one. I'm not sure, it's not quite right because there's this funny area, but just ignore the funny areas right here. So the outer one is like the initial hypersurface, and then the inner ones is at later time. And you see that this here, this is right after, this is right before it had pinched off the neck. This here are the time slices right after. And so just because it keeps moving inside itself, you can define something that's called the arrival time function. And the arrival time function is just defined on the domain that the initial hypersurface bound, and it's just the time when the hypersurface arrives at that point. Okay, so the arrival time function is just, you think about standing somewhere, and now the value of the function is just when the hypersurface comes sweeping through. It will pass through in one direction, so it doesn't come back. So this gives you a well-defined function, and that's the arrival time function. The arrival time function has, it's just an aside, it has a game theoretical interpretation due to Bob Cohn and Sylvain Serpenti. And it's a game that was actually invented, so they discovered this in 2006, but it was an old game invented by Joe Spencer. So he looked at a family of games. Here I'm just illustrating it in 2 dimensions, but it actually is in all dimensions. And he have like a family of games that he called balancing games. And some of these games, one of these games gives you the mean curvature flow as a limit when like the step size goes to 0. Okay, so now let's also recall, so this here is, so if you're looking at the shrinking spheres, so we saw that if you're looking at spheres of radius square root of minus 4t, where t is negative, this 1 parameter family, this is in R3, similarly in higher dimension, this 4 is now changing depending on the dimension. But this 1 parameter family of spheres are flowing by the mean curvature flow, and this just means that for the shrinking spheres, the arrival time function is given like this. This is the arrival time function normalized so that the point where it becomes extinct is the value of the function is 0, right? This just corresponds to that time is 0. Similarly, for the shrinking round cylinders, if they are rotational symmetric around the x3 axis, then the arrival time function is given as this quadratic polynomial. Right, and again, this corresponds to that, so the cylinders that are rotational symmetric around the x3 axis, right, they will disappear in this straight line where x1 and x2 are 0. Right? And so, right, so critical points, so the simple observation that one can draw from this just on a functional theoretical point of view is that the critical point here for the arrival time function are exactly when the flow becomes singular. Right? The critical point for this function here on R3 is the origin. The origin is exactly when the flow is becoming extinct in a point. Similarly, for the shrinking round cylinder, the critical point here is where x1 and x2 are 0. This is the x3 axis. And this is exactly where the flow becomes singular in the line. Right? And so you also see that this is maybe a little bit hard to say because it's kind of it's so obvious in this case. But you could of course think about this quadratic polynomial. It's a critical point. So this here is kind of like this Taylor expansion of the function. Right? This is, if you think about the Taylor expansion of the function, near, in this case, near the origin, then this here is the only term that should be there, right? Because it vanishes at that point, and the gradient also vanishes, right? So this is like the second order Taylor expansion. Okay. So now the equation. Right, and so what is the equation? So if you're looking at a function and you're looking at the level set of this function, then of course the normalized gradient, this here is the normalized gradient, that's a unit normal. The mean curvature is just the divergence of the normalized gradient, so this here is the mean curvature. The level set will move with speed 1 over the mean curvature. And this gives you that the arrival time equation is this here. And there's a slightly more convenient way of rewriting this. And this is how you do it when you want to make sense of it in the viscosity sense. And you rewrite it like this. So you write it as a Laplacian and then minus the Hessian in this direction. Right? Remember again that by the avoidance principle, yeah.
So the arrival time is that I fix one hypersurface and I think of the arrival time at each point.
Yeah, if you fix a hypersurface and you want to study the evolution of it, right, then you take a function that is 0 on that. The arrival time function would be, or whatever. I mean, if you want it to be, so typically now in those examples before, I normalized it to be 0 at the singularity. That was just because I had one singular time, right? But this is just a time adding something to time, right? So you could think about the initial one as where the function is 0, and then the later hypersurface is at the time when it arrived there. Right, and so this is how you rewrite the equation. And so I just want to remind you that when you take any closed hypersurface by this avoidance principle, we know that it becomes singular. That it will be singular is actually, it's not so hard to see that a singular point is equivalent. So geometrically, we talk about that the flow is singular, the hypersurface is not smooth. Analytically, it just means that the gradient has a critical point at that point, right? So critical points are the same analytically correspond to singular point for the flow. And we know that if you take any closed hypersurface, we know that it eventually will become, that you will reach a singularity by the avoidance principle. So you know that the gradient will vanish. This of course also trivially corresponds to that if you took the function to be 0 on the initial hypersurface, then there must be a maximal inside, right? So of course there must be a point where the gradient vanishes. But so of course, and this here of course is, so here we've written in this way, and again this is what it means for the equation to be degenerate, that you're forced to divide by 0, right? And so again, Evans and Spoke, Chenkig and Godot, they proved that solutions are Lipschitz. Tom Ilmanen proved that, so he gave an example. It's actually an example exactly like the one we looked at so this was in his thesis. He proved that if you take a particular rotational symmetric dumbbell that have an additional reflection symmetry, then the arrival time function is not C2. So in general, it's not C2. Now, here's the optimal regularity. There's a second part to this result. So it turned out that Chenkig and Godot, Evans and Spook, they were able to prove that solution for always Lipschitz. Well, it turned out that actually solutions are always twice differentiable. They're always twice differentiable. And at critical points, the Hessian matches exactly the arrival time, the Hessian of the arrival time function of the shrinking sphere or cylinder. I state this as if it was an R3, but it holds in all dimensions. Okay?
So the equation is to be understood in the weak sense.
Yeah, that's right. I mean, the solution, well, that's right. But we see, I'll get to this the next, if I...
Okay, so it's a differentiable, but the second derivative need not be continuous.
That's right. It's right. And in fact, and we'll get to this in just a second, the function is, so the optimal regularity turned out to be that the function is always twice differentiable. It is C11, it's C2 in cases that you can completely describe geometrically, and we'll come to that. That's a second part to the theorem. But then again, my plans for this talk today and tomorrow. So today I'll talk about this. Tomorrow the hope is to talk maybe a little bit about the proof, and I also want to talk about something I was alluding to yesterday. That somehow, we have this equation here. This equation here, it's an elliptic equation. So obviously, like all elliptic equations, are kind of modeled in a way by the Laplace equation, right? It's a nonlinear equation. For the Laplace equation, or for an elliptic equation, a non-degenerate elliptic equation, if it had analytical coefficient, then solutions are analytical. So there was this hope so it turned out that solutions are only twice differentiable, but there was this hope that you still could have that solution behave like they were much smoother. Even you could hope that they behaved as if they were analytical function. And it turned out that in some sense they do. They're only twice differentiable. You can classify. Anyway, but so I'll talk about a little bit about that tomorrow. And then again, I will also talk about how, these circle of idea, you may be able to prove optimal regularity for other equations using them. Okay, so now, so again, sorry, that was exactly what Spiros said. He was a little faster than I. So now once you know that the function is twice differentiable, and actually you understand the Hessian, you know what the Hessian is. So the Hessian becomes very, very simple in these cases at the critical point. Then actually you don't even need any more viscosity solution. Of course it is still a degenerate equation. You can't do anything about it. But now it's kind of obvious what it means. You make sense of what it means to be a solution in a classical sense. Okay. So obviously there have been many other later on, but this was like one of the early main application of the notion of viscosity solution. A second derivative exists, it may not be continuous. Just a little bit about earlier work. In the convex case, so if the initial surface is convex, if the initial hypersurface is convex, then Huisken proved almost 30 years ago that the arrival time function is C2. Bob Cohn and Safati, they proved that in the plane, when you're looking at the curve shortening flow, the initial curve is convex, then the arrival time function is C3. And Natasha Sessom gave an example of a convex hypersurface in the plane, convex surface in R3 actually, where the arrival time function, so by the result of Huisken, it's C2, but Natasha proved that it may not be C3. So, okay. And so here's the second part to this optimal regularity. And so they say that if the arrival time function is C and again I state this only in R3, but its same result hold with kind of obvious changes hold in all dimensions. So the arrival time function is C2 if and only if it only have one critical value, and the critical set is either a single point, and in that case the Hessian at that point is a constant times the identity, or the critical set is a simple closed C1 curve, and the Hessian here looks like the Hessian of the shrinking round cylinders. So it only have two eigenvalues. And so in the second case, the kernel of the Hessian is exactly the tangent direction to this curve. Again, this result holds in all dimensions. So in higher dimension, it's not a curve. You're getting a k-dimensional closed k-dimensional manifold. It's always C1, and k could be anywhere in between. Right? And so if you think about it, the example of the sphere, this falls into the first category where there's a single point, there's a single critical value, and the singular set is just a point. The case of the cylinder fall into the second category, where, the cylinder, of course, is non-compact, so you don't get actually a closed curve. But there's, again, a single time, and you're getting this line, and the ring here, the marriage ring or wedding ring, it's also fall into the second category, right? Because in that case, there's also just a single critical value, and it became extinct in this round circle, right? So the whole circle was a singular or critical set. On the other hand, of course, the dumbbell doesn't fall into under this, right? Any dumbbell, right? Not just the one that was reflection or symmetry, but any of these, even this larger class of even very general dumbbell wouldn't fall into any of these, because there wouldn't be just one critical value, right? There are several times where you are getting to singularity. So you see that the Tom's example, this, sort of a corner of this, of course, give you that the example that Tom's look at, the arrival time function, of course, is not C2.
Can it also be made local? So you can speak about C2 in one.
Yeah, that's right. That's right. So that's right. So this result here, this result about optimal singularity is for this elliptic. A lot of the proof actually work more generally. If you're asking for a truly local version of it, then I don't know it. There's some small technical reason for it, but a lot of, I think the main. There's if you were looking at so we're looking here at the elliptic degenerate equation. If you're looking at the parabolic degenerate equation, it's kind of clear what the optimal regularity is. A little bit more complicated, but it's clear what the statement should be. I can talk a little bit about that later, but that kind of will require me to talk about something else too. Okay, so what are the key ingredients here in the proof? So twice differentiable, of course, one way of thinking about it is just meaning that the function is, so you only need to check that it's twice differentiable at critical point. But you only need to check it where the gradient of the function vanishes, because if the gradient doesn't vanish, the equation is not degenerate. So it's kind of classical that. So you only need to check it at critical points. Now, so at critical points, it just means, so twice differentiable means that it's that the function looks like some quadratic polynomial plus, say, higher order term, right? And so what you want to prove is that this second order approximation, that this quadratic term is, or the second order approximation, is the arrival time of the shrinking cylinders. So it suggests that the level sets are approximately cylinders, and we know that already. The key problem here is a priori, again, as we mentioned earlier, that the cylinders could change. As you're moving in closer to singularity, the cylinders could be different cylinders as you're moving in. So here, this picture here is supposed to illustrate that you have some singularity. It's kind of in the middle of this, say, so just imagine that the singularity is at this point here in the middle. Just imagine there was just one singular point here. And so imagine that at some time shortly before the hypersurface, if you rescale, then you're getting the yellow cylinder. If you now look at a slightly later time, you get that the hypersurface kind of in a neighborhood of that singularity would look like the blue cylinder. At an even later time, it would look like the red cylinder. Right? The problem here is that the axis is rotating around as you're approaching the singularities. And so a priori, this could happen. If it could, then that would be a big problem to prove twice differentiable. And the key here is that it turns out that this situation here, where it's changing from scale to scale, is impossible. And so this uniqueness here, again, is the key to being twice differentiable. And so it's said by that again that as we sort of zooming in to the critical point, the level sets are spherical, cylindrical, and we want to somehow read this off of the Taylor, second order Taylor series. So this kind of uniqueness that this illustrates here is a kind of classical problem in geometric analysis, whereby some relatively weak notions you can use some sort of compactness theorem, and to get that if your blow-ups are nice, but the problem is with those methods they allow the possibility that blow-ups depend on how you're blowing up. Okay, so the methods, I mean, sort of roughly speaking, goes that if you take a sequence of blow-ups, then there's a subsequence that converge, but you may have to pass to a subsequence that allows for some sort of non-uniqueness. Okay, so that's a kind of famous problem in geometric analysis. There's a lot of important work on this. There's some important work of Allard and Almgren and Leon Simon in the early 80s. Here the key problem here is, and so this is a problem that makes this here particularly difficult. But this is also the only case of it, though, where uniqueness has been completely resolved. I mean, there's no general case where it has been completely resolved before this one. But the problem here is that the blow-ups are non-compact. Right? We're getting these non-compact cylinders. And so the non-compactness, that's a big headache. Okay. Right, and so of course this sort of non-uniqueness, you should compare it. So it's kind of natural that you come in when you want to prove that a function is twice differentiable. It's natural because even if you were just trying to prove that a function was differentiable, then you would say, okay, when is a function differentiable? One way of thinking about it is that on all small scales, it looks like a linear function, and that linear function is the same on all scales, right? If it looked like a different linear function on a smaller scale, right, then there was no derivative at that point, right? So, and this here is in a way similar at a second order level. Okay. Okay, and so again, so it turns out that cylindrical blowups are unique, and this is the key step. And this means that every blowup, if one blowup is a cylinder, every other blowup is a cylinder. The axis has not changed; it doesn't rotate around. The proof here uses, and I'll talk a little bit about that tomorrow. It uses a kind of Weiershevitz type inequality. It's very different, though, from other Weiershevitz type inequality, and I'll try to explain that. But it's inspired by the Weiershevitz inequality. I'll remind you, or I'll tell you about what that is tomorrow. That was proven in Weiershevitz around 1960. Earlier results on this kind of uniqueness was proven by Gang, Knopf, and Siegel, Gang and Knopf, and Gang and Siegel. let me talk a little bit about the key, key to prove. I just want to say a few words. So this optimal regularity, it has two parts. It has part one is that solutions are always twice differentiable, and then it has a second part that characterizes when solutions are C2. So let me just say a few words about how to characterize solutions that are C2. So again, we're looking at this degenerate equation, and the key here is that C2 is going to be implied. So the particular form of the Hessian that we get at a singularity will imply that the axis axis of the cylinders are nearly the same at nearby critical points. So let me just say a few words, just very briefly. So why is this example here of a dumbbell not C2? Well, the thing is that you're sort of looking at the Hessian here, because now we know exactly how the Hessian, in not just in this example, but just in complete generality, we know how the Hessian is going to be twice differentiable. We know exactly how the Hessian looked like at a critical point. And the thing is that if you want to look at right before the singularities, you want to look at a point here. And the Hessian here, because we know how it looks like, it will look like exactly like the Hessian of the arrival time of a shrinking cylinder. And then you look at a point at this tip right after the singularity happened. And the Hessian at those points will have to look very different from the Hessian of the arrival time of the shrinking cylinder. That's somehow the essence of that. I mean, obviously, it's somewhat more complicated to actually carry this out. Okay, and so that's but this analysis, how do you do this? It also it requires you to have smooth points. This analysis requires us to have smooth points nearby. So why? So you can ask. So you have this singular point. Why do we have a smooth point nearby? So why is this kind of point smooth? And so why can you use this argument? And so this leads us naturally into talking about what about the singular set for the flow, or if you will, analytically, what about the critical set for the flow? And so on that, we have some sharp bounds for the set of singularities. Just again, let me remind you that the simple examples we looked at, the sphere, cylinder, marriage ring, the singular point was either for the sphere, it was a point. For the shrinking round cylinder, the singular point was a line. The marriage ring, it was a closed curve. And in these three cases, the singularities occur at just a single time. In the case of the dumbbell, we get three points that were singular, corresponding to two different times. That was just because we were looking at this dumbbell that had this additional reflection symmetry, where the two bells have the same size. Okay, now the singular set is, of course, in geometric term, in analytical term, it corresponds to the critical set of the function. In geometric term, it's where the flow of the hypersurface is not anymore smooth. In R3, similarly in higher dimension, Brian White proved in 2000 that the space-time dimension of the singular set is at most 1. This proof uses dimension reduction, and this is parabolic. So this is used parabolic scaling or parabolic distance, where the time axis acts as if it has dimension 2. So this is R3, similar in higher dimension. A consequence of this is that in R3, almost every time is regular. But this is just in R3. Okay. and so using, and again, the key for this is actually this uniqueness. We can prove a kind of optimal, or near optimal regularity result. So again, so this is this here is stated in just our tree. The singular set is, but similar thing hold in higher dimension. The singular set is one version of this, but it actually is kind of much finer than this. That the singular set is contained in the finite union of compact C1 curves plus a countable set of points. So we prove this, and so in particular, right, the one-dimensional Hausdorff measure of the singular set is always finite dimensional, just like in the case of the marriage ring, where the singular set is this simple closed curve. This is just in three-dimensional, similar in higher dimension, where you're getting n-2. If it's in Rn plus 1, you're getting R n, right? If it's a hypersurface, n-dimensional hypersurface in Rn plus 1, then you're getting this n-1 for the n-1 dimensional. But it's much sharper than this because it also gives you for all kind of lower stratifications. And I can tell you a little bit about the proof, because the proof is actually, sorry.
So the C1 curves are closed and they're bounded?
No, and this is, so that's right. And so I was saying that it's sharp, and it is sharp, but of course, and we'll talk a little bit about this, it is sharp. But there's still more you can hope for. So what we cannot rule out, for instance, that it's like a line segment that ends, okay? And we cannot rule out, we also have to allow this countable thing. And it's a very interesting problem, and I'll talk a little bit about that, because it's somehow tied in very nice, I think, with what I'll talk about tomorrow. But otherwise it's sharp. Right? And again, uniqueness here is the key for that. So I'm not sure I can even talk about. Right, so just a few words. Right. Yeah. So this is just that in higher dimension you get a similar statement here. And it uses a kind of parabolic version of parabolic Reifenberg property, where that uniqueness of the cylinders allow you to basically project onto the axis. You have a well-defined axis of the cylinder, and what you actually are able to prove is that the singular or the critical set is actually like a Lipschitz graph over the axis of the cylinder in a whole neighborhood of that singular point. And this uniqueness of axis allows you to, have a well-defined axis, allow you to project onto the axis, and giving you this, I think, nice structure. Okay, so I should stop here. It's 1:30.
What happens in non-mean convex case?
So in the not mean convex case, yeah, that's right. And there is a version of this. I mean, there's not a version of this, but there is a conjectural version of this. And maybe I will talk. I mean, there was, I keep being way too optimistic for what I can cover. And so in general, it's not actually twice differentiable. So it's not, in general, it's not twice differentiable. But what should be the case is that if you're looking at, if you take a hypersurface and you perturb it ever so slightly and you run the flow, then it should be twice differentiable in generic. And so we know a lot of pieces for this. But but we don't know all of them. But the uniqueness, that is the key. The uniqueness, it does not depend on mean convexity. The uniqueness just say that if you have one as singularity, and if the blow up is a cylinder and have nothing to do with mean convexity, if the blow up is a cylinder, then all of the blow up at that point is a cylinder with the same axis. Okay, so it doesn't require that the hypersurface is mean convex. And the other thing we have is that the only singularities you cannot perturb away, those are actually cylinders and spheres in all dimensions. We also know that.
You cannot interpret straight surfaces as level sets of some function.
Yeah, you can. I mean, that's right. You can. And I mean, so we just talked about here. The arrival time function is, it's very natural. But of course, you could, if you're looking at the level set method, the level set methods also works if it doesn't move monotone. It doesn't give you an elliptic equation, but it gives you a parabolic equation. And it's just that all of the level sets are flowing by the mean constant flow. You're getting a degenerate parabolic equation, and for this degenerate parabolic equation, you should have this similar, but now you need some generic condition. In general, it won't be true. I mean, there's simple examples we can talk about that where it's not true in general. So you definitely need that.
So the projections of some level sets.
No, it's just. I mean, there was that picture earlier that Walter was referring to. I mean, that was supposed to illustrate the level set. So now it's a level set of a function that depends on space and time. And you're tracking a function of space and time, and now you're fixing the pre-image, right? So for each time, right? I mean, so you're looking at pre-image, right? So now you see there's like three parameters. There's space, there's time, and there's the value of the function, right? So you have one, in the general case, you have one more parameter. But it's like all values of this, like the level sets for of this function depends are flowing by mean. I hope that's clear. So.